if it is, does it have asymptotes? It's going to make knowing domain and range so much easier if you can kind of recognize by looking at the equation, oh, that's going to always have this kind of domain or this kind of range. So let's just start right here with piecewise functions. A piecewise function is really just a function that is in pieces, right? You're not graphing the full function. It's a restricted domain. They look kind of scary, especially if you have more than two pieces, but it's really just understanding what it's saying is the important part. So I just put graph is in pieces and domain is restricted. So they always have a function is equal to, and they use that little bracket to put them together, and we're just going to do two pieces, but you really could have more pieces of your graph. And they give you an equation, and then usually there's a comma right here, and then they tell you where you're allowed to graph it. You're only allowed to graph it when x is less than or equal to -4, and then you're going to graph this equation, but you're only allowed to graph it when x is greater than -4. The big thing I want you to know from this is when you graph this, it should still be a function. It should still pass the vertical line test. So if it doesn't, something has gone wrong. You've graphed something incorrectly. And so that's an easy way to check that you've done this right, is by checking that it still passes the vertical line test. So I'll hold tight for a minute as you get this written down. Maybe make a nice little graph for yourself. For me, I start with this, right? This tells me where my graphs are going to start and stop. It's kind of like the dividing mark. So at -4, right? Like right here is where it starts and stops. It's not an asymptote, but if it helps you, you can kind of cut your graph in half. So if it helps you and you want to put like a dotted line down your graph, just to kind of help you know that your graph should be on either side, you can. You don't have to. It's not like an asymptote that it can't touch it, because it is going to touch it. But this is kind of like our starting part, so I'm just going to kind of mark it as I go through here, but you can make a dotted line there if you want. So for this one, I could graph the line x plus 1, and I'm going to graph the whole thing just for a second so you can kind of see what we're doing here in case you forget how to do these. But x plus 1, don't graph this, but that would be a y-intercept of 1 and a slope of 1, right? And so you would get, oh, I did that backwards. Right? It would be this entire line if it wasn't a piecewise function. But the piecewise part says you can only have it when x is less than or equal to -4, which means it can only be on this side. So the rules of graphing haven't changed. It's just changed where I'm allowed to have it. So that means I'm not allowed to have it on this side of the line, right? I can only have it starting when x is -4. So one thing you can always do is you can actually graph it and just go back and erase the part you don't need. Or maybe the easier thing to do is just plug in the point where it starts. Plug in -4. -4 plus 1 is -3. So at -4, it's going to start at -3 and then do your slope, which would be going that way, down 1, back 1, down 1, back 1. And notice I filled in the circle because it's included. And for 1/2 x minus 3, that's on the other side of -4, which means, again, you have some options here. It's over here, which means if you want to graph it the way you've always graphed, where you do the y-intercept is -3, and you do the slope is up 1, over 2, up 1, over 2, you can do that. But the big thing is, it's got to get all the way back to where it's allowed to go, like all the way to, oh, that's no good. I'll just head on to it. So I think sometimes the easiest thing to do is, again, if you just plug in -4, you would get negative 2 minus 3, which means at negative 4, I would be here at negative 5. Does that make sense? Why did I put an open circle? Because it's not included. Starting at negative 4, not included. Again, you could get there by going down 1, back 2, down 1, back 2, however you want to do it there. And it would be going in this direction forever. Notice that it still passes the vertical line test because at that negative 4, one of them is filled in and one of them is open, which means it's still only touching it one time. That's why it's always like that. Questions about that? What would the domain of this be? All real numbers, because although we stopped at negative 4, every number over here is used, negative 4 is used, and every number over here. So the domain of this is still all real numbers. What about the range of this? Are there any y values that aren't used? I don't think so. You might think that, well, there's a gap here, but notice that this side's going to cover those numbers that aren't included, and this side's going to go up, and it's also going to cover those numbers that aren't included. That any y value that you could pick, there's going to be a point on those graphs, one of those graphs. So the range is also all real numbers. Right? That's not a continuous graph, though, because you'd have to pick your pencil up, right? So that's kind of the definition of is it continuous or not. It's not, because there's a jump there. Yes or no? A little more exciting than just linear equations here. So, worst case scenario, you make an XY chart for these equations. Best case scenario is you kind of have an idea of the shape of them and what they look like, and maybe you don't have to make an XY chart every time. Remember that you're only graphing a piece of each one of these. And for this one, it starts and stops at 0, which x equals 0 is just the y-axis. So that means half of our graph is going to be on the left side of the y-axis, and half is going to be on the right side of the y-axis. X squared plus 3, what kind of graph is that? A quadratic, a parabola, right? That U-shaped graph. If you aren't sure what's going to happen there, you can just pick some points. Plug in 0, and it's greater than or equal to 0. So plug in 1, plug in 2, see what happens. Okay, so for this one, I plugged in 0, 0 plus 3 is 3. If I plug in 1, 1 plus 3 is 4. If I plug in 2, 2 squared is 4 plus 3 is 7. It is included, so 0, 3 is going to get a solid circle. 1, 4, 2, 7. You know it should be a quadratic. You know it should be a parabola, so make sure that your graph is looking like that. I'm only getting half of the parabola, though, because this piecewise is telling me I don't get to graph the other half. What kind of shape is the second part of that graph? Absolute value, and what kind of shape are absolute value graphs? V-shaped graph. Again, it's only half of it, so it's going to kind of just look like a line. Again, if you're not sure what it's going to look like, make an XY chart. My goodness. This is long, dangling sleeve. Again, I'm going to pick 0, even though 0 is not included, but I need to start there, and I'm going to go left, so I'm going to pick 0, negative 1, and negative 2. And if I plug in 0, 0 minus 2 is negative 2, but absolute value is always positive, right? So that's positive 2. Negative 1 minus 2 is negative 3, but absolute value positive. Negative 2 minus 2 is negative 4, but it's just 4. So 0, 2, open circle because it's not included. Negative 1, 3, negative 2, 4. And the absolute value is just a V. It's just basically two linear lines that formed a V there. So that's just going to go straight up like that. Is this graph continuous? Definitely not. Close, but they don't match up. So it's not continuous. What sometimes happens is, what if that line would have started right there on that solid dot? And people say, well, how do I do an open circle on top of a closed circle? Well, it's just not open anymore, right? Like if you have an open circle and then a closed circle, it's just going to be closed now. That could be a continuous piecewise function if the pieces actually meet up. But that's the kind of stuff you're going to see on your homework today. Nothing crazy. Mr. Gressick and I were talking in the Algebra 2 book. The piecewise functions are like out of control of what they give you to graph. These are just pretty basic. They just want you to understand what to do and how to think about them. Would the domain on this be the same as the last one? Would the domain still be all real numbers? And again, look at each piece. This side's going to go this way forever. This side's going to go this way forever. So I think my domain here would still be all real numbers. What about my range on this one? Would my range be all real numbers? Definitely not, right? Where does my range, well, anybody want to give me a range? Including 2? Not including 2. Because 2 is not included, but every number after that is. So even though there's a little gap there, again, it's going to still have a value that goes with it. Sometimes the range on these can get really crazy if it's really complicated. I remember in the Algebra 2 book, some of the ranges were like just like a random number, one number, and then an interval from there. But these, the two that we've done here, and the ones in the book are similar to this. Their domain and range aren't that crazy to do. Questions about that? Piecewise function is not really one of the 10 basic graphs because it's just combining those 10 basic graphs. It's just piecing them together. So that's why it's kind of its own separate thing from there. Maybe you remembered how to graph these from transformations and you didn't need this chart. So very briefly, I'm going to remind you of the transformations today, and we'll talk more in depth about that next week. But just in case you remember, do you remember what happens when there's a number added or subtracted outside of the function? What does that do to your graph? It's a vertical shift. So if you remember what x squared looks like, and you know that just means it moves up 3, like that's why you could just move it up 3 and make the same graph. Whereas a number inside the function, added or subtracted, what does it do? Did I do this right? Yeah, okay, sorry. Just having a moment. That's fine. It moves it horizontally, which was why I was having a moment, because it looks like I've just moved up 2. But the thing is, if we kept going here, this would keep going like this, and that would be where it would have turned, right? Like that would have been the vertex, kind of. So when you move it, or add or subtract inside the function, it moves it horizontally, but it's like the opposite, right? So minus 2 actually means it would move right 2, plus 2 means it would move left 2. Those are very useful things because it helps you when you're graphing that you don't have to make XY charts. Also, we have the whole stretch and shrink thing, or compress and, I don't know what the other word is. They use stretch and shrink in this book, but the Algebra 2 book uses compress and stretch, maybe? Where you can know that it's going to like make it skinnier parabola, or it's going to stretch it out and make it look wider as we do that. So I think very wrote these out. Oh, I didn't write them out. If you want to write them out today, or maybe you just remember them. And again, next week we'll talk about this more, but I do expect that you'll learn these by the end of the chapter. But today they're just kind of helpful. Like, it's an easy way to graph. So again, adding and subtracting inside is a horizontal shift, plus actually means that it moves h units left, and this one is h units right. So this would mean like inside the square, inside the cube, inside the square root, inside the absolute value, like inside the function. Whereas outside the function is a vertical shift. So this is h units up, then this is h units down. And then the stretch and the shrink I'm not really going to focus a lot on today, but that's when there's a number multiplied in front of the function. But it depends on, is it vertical or is it horizontal, right? It's all about like if it's 2 times f of x or if it's f of 2x, right? Like it's all about whether it's inside the function or outside the function and all these rules that come with it. I'm just going to write stretch, shrink right now, and we'll talk about that more next week. Worst case scenario is you're just making XY charts right now. Hopefully you at least know what shape it's supposed to be. If you remember some of this stuff, then maybe you don't have to make the XY chart every time because you remember, oh, that's just going to be the parabola moved over to or down to. And again, we'll focus a lot more about this. What's really cool about these transformations is it works for everything. Every type of function that we talked about yesterday, these transformations work for. Next semester when we talk about trig, sine, cosine, tangent, all these graphs that you've not done before, these same kind of rules still hold true. We just maybe have new names for them, but it's still a vertical shift. It's still moving it horizontally or stretching it or shrinking it. And so if you know these, it applies to every type of graph that you're going to do. So on your homework, it talks about using a graphing calculator, but on my homework, I said, I want you to graph these by hand. I think it's, some of these basic ones, I think that it's important that you can make a decent graph, and that you can give the domain and range of it. So again, I just want you to recognize of the 10 basic graphs, which one is it? What shape should it be? Worst case scenario, you're making an XY chart. So what kind of graph is this? Quadratic? Parabola? So if you don't know what that plus 3 inside means, that means you got to make an XY chart. If you do know, what does it mean when I add 3 inside the function? It's moving left 3 units. So instead of normally starting at 0, 0, I can move left and know that I'm going to be starting over there. And you can check that really easily because if you plug negative 3 in there for x, you're going to get 0. What's really great about transformations, except for stretches and shrinks, is that the shape stays the same. So if you know normally a quadratic, right, I don't have to draw this, but normally you do, I'll do a different color. You do 0, 0, and then if you plug in 1 and negative 1, you get the same thing. If you plug in 2, you get 4, and negative 2, you get 4. Right? It's a very nice parabola. The same shape is happening here. We're just moving it over 3. So the reason that I like transformations is I don't have to do the computations anymore. I can just say I know when I go over 1 from that new vertex, it's going to go up 1. And again, you can check very easily, plug negative 2 in there, or negative 4. And I know if I go over 2 from there, like normally when I go over 2, I go up 4. If I go over 2, I'm still going to go up 4. And I get that exact same shape, just shifted over 3 units. I'm not saying you have to make 5 points, but I'm saying your graph needs to be accurate. So that means when I'm grading this on a test or a quiz, if you just make 1 dot and you just wing it from there, if I go over 1 and up 1, I better be able to put a mark on your graph there. And if I go over 2 and up 4, it should hit there. Does that make sense what I'm saying? Like, I want you to know that that shape is there. So I don't want you to just be like this, right? Because then if I go over 1, up 1, I'm going to say you missed that point there, right? You made that way too skinny. So it doesn't take that long to make those points if you know the shape that it's supposed to be. And when we talk about stretches and shrinks, we'll talk about how if there's a 2 in front of it, what does that mean? That I can figure out what that means instead of going over 1 and up 1. So be accurate, be nice, smooth curves. This is not an absolute value, so I don't want to see like a pointed V on that. We can make nice graphs. And I even have graph paper if you really want some. Hopefully this will help us feel better with domain and range if we're struggling with it. Yesterday we said the domain of x squared is all real numbers. Is the domain of x plus 3 squared all real numbers? Yeah, we just moved it over 3. It's the same. Yesterday we said the range of just x squared was 0 to infinity. Has my range changed? No, because I kept it the same height. If I would have moved it up or down, my range would change. But if I don't move it up or down, then my range hasn't changed. Questions about that? I think maybe I have one more. Maybe not. Oh, maybe not. Hopefully you did up through 24 yesterday. So this is continued homework 1.3. It's not that many more problems. 29, 30, and 33. The directions in the book say to use with a calculator, but I'm saying do it by hand. 33 is a step function, so we can talk about that one. Definitely, but think about plugging in numbers and when would it go up a step, or when would it, how long would the steps be? Kind of a tricky one. And then 45 and 50 are also graphs, piecewise functions. So that's 5 graphs. If you want some graph paper, I can give it to you. If you want to make your own graphs, I'm okay with that too.